Okay, so how is the homework going? Homework 4. Finished? Huh? No?
Almost.
Hey, Bobby, you look different today. You shaved?
I shaved.
Yeah, I'm very young, right? Young,
Yes.
10 years younger
Thank you.
than yesterday.
Thank you.
I'm kidding. Okay, so so give me the homework for Friday by Friday evening, okay? You can do that, right? Because I give you the detailed the derivation and only leave some intermediate steps that you need to fill. I think they will not take you too much time, but I want you guys to know understand this derivation. What? As I said, this course level is very high, but we don't have too much time, and also Abacus, we do not have access to Abacus, so there's a lot of change this semester. So let's continue our talk. We are in good shape. Our progress is very good, and we are in good shape. No worries. So last time we talked about the J testing of metals, J testing of metals, and we talk about this is ASTM protocol 1820, and we also have talked about the GIC and how to calculate the GIC, how to get the GIC, measure the GIC, and we have two methods: measurement, direct measurement, or the compliance. But compliance means that, and we after we have the correct body, and we will keep loading it, and then at some point, and we just unload it, and then we will see the unloading curve. We see loading, unloading. We keep doing this, and for each of these unloading, and we will find that the stiffness, the slope, that becomes the slope of stiffness becomes smaller and smaller. That means the compliance C becomes bigger and bigger because compliance and stiffness they are reciprocal to each other. Do you guys agree? Compliance and stiffness they are reciprocal to each other. So we also talk about this is the polynomial. The C is a function. This is AW is a polynomial, okay? The C is a function. C is function of the C, and AW has AW here. How to calculate this AW? And for this example, for compact the specimen. And what is a compact specimen? Can somebody tell me what is a compact specimen, guys?
What's a specific type of geometry? Is it the one with the circle in it?
Yeah, compacted specimen is the specimen we use in the quiz modeling, right? And we totally talk about 5, but that one is used in our daily the quiz modeling. For all other the specimens, we have SENM. SENB is a single edge notched the bend specimen. That is, we have a beam, we have a single edge, and we bend it. That's SENB. We also have a disc, and we also have an arc. And the 5th one is the tension. The tension means that this is a specimen we have a through thickness hole. Okay? Through thickness hole we have the tension. So we totally have 5 different specimens. But here we focus on compact and SENB. And you can just use the direct measurement or compliance measurement. And you can also measure the crack length using the potential drop method. And do you guys still remember what is the potential drop method? As the name suggests, potential drop means the voltage potential drop. Can somebody tell me, refresh your memory, what is the potential drop method? Okay,
Like, take a specimen, measure the voltage difference across it, and as the crack increases, the voltage difference will change.
yes, yes. Okay, so you can look at your, I can just draw this one schematically. So you should know this is the voltage potential drop. And potential drop is this one, and this is what we have learned. And suppose without loss of granularity, we use the compact specimen. And so here, so this one is a notch. Here is we have voltage, we have battery. On these two ends. Okay, so this is a crack. So this as long as the crack grows, if the crack grows, so that means the ligament becomes shorter, right? Ligament becomes shorter means that the resistance becomes bigger. You guys agree? Right? So that means intuitively, that means if this ligament is shorter, I don't know. I'm sorry. Very briefly. Sorry, guys. So we know that if the ligament decreases, this will be more difficult for these electrons to go through from here and here, right? That's the reason the resistance goes up. The resistance goes up, but the voltage does not change. You can see on how this is a crack grows, and how this is voltage from here to here, and they grow, and how they change. You will know, and how the crack grows. Understand, guys? This is a voltage potential the drop method. So this is current. Current. When we calculate the J, we can decompose J into the two parts. One is elastic part, and one is the plastic part. And for elastic part, we know that the J integral equals the K squared. This K is elastic, the stress intensity factor K, divided by this is the effective Young's modulus, right? Effective Young's modulus. As I said, when we do the experiments to get this is a GC and KC, and we need to use plane strain, right? Underscore this one, plane strain. If we use a very thin the sheet, and the results will not be reliable. And we need to use a thick plate. And as a result, the same plate is condition we call plane strain. So for plane strain, and this is effective Young's modulus equals 1 minus nu squared divided by the nominal Young's modulus E here. Right, so this is, we use this equation and to calculate the GEL, the elastic part of J integral. So you can see K is inferred from the load and the crack size through the following equation. So this equation, right? So this P is a load, and B, what's the BS?
Thickness.
Yeah, B is thickness, W is width, and we use this equation, and here is a polynomial. F is a function of the polynomial function, and in terms of the ratio of this A and to this W. So we use this equation and to calculate the Ki, and that's for the elastic one. However, if we use a side grooved specimen, and we use another equation, right? So this equation equals P B N W and multiplied by this one. So do you still remember what is the side grooved specimen is? get a set grooved specimen? Huh? You know that, right? So this is a plate, and this is a plate, let me draw it. So this is a plate. Okay, here is a crack, right? So here is a, this is a crack. Suppose this is a crack. And we want to, this is a dotted line. So here I just draw this is, this is the true line. And here is a B. This is a true thickness. And however, along this line, I just set groove it. Is a set groove it. And set groove it. Oh, I'm sorry. I'm not good at drawing, guys. Forgive me, okay? And set groove it. You just remove this material. On this side, you also set remove this material. So here, and this is the BN. So this is nice thickness. And I want you guys to take a look at the set groove specimen. And also, I want you guys to know why sometimes we need to use this one. The reason we use the set grooved specimen is that we want to enhance the triaxiality this stress state. Good. So I want you guys to look at the lecture notes and to know the benefits we get if we use the set grooved on this specimen. So this is equation, okay? And some students might ask, where can I get this as F function? And you just go to the textbook, and go to the table, you will have this is the F function. And now we focus on the GPL, the plastic J, because the more elastic J can be obtained using either this equation or this equation. And now we focus on this plastic part, right? So the basic procedure in ASTM 1820 includes a simplified method for computing GPL from the plastic area and load displacement curve. So here, how can we do that? So here, this is a figure I show on the handout. So this is displacement, this is a load. If we draw a figure this way, okay, and if this is the elastic, and then the material yields, and this is strain hardening, and then after some time, and you just go down, unload it. After you unload it, and here part of this is a total displacement, and will be recovered. However, you will have this is residual displacement. Okay, so this is some people wanted to use this kind of figure, but the last time I told you that this figure is not exactly, I should not say that. And this is analogous to the figure of stress and strain. What? Understand, guys? I told you guys. So this one, we have epsilon and sigma, this curve. And epsilon and this curve, we also have at the very beginning linear elasticity, then the material yields, then strain hardening, and then you just remove the load, and then you will have. So this one is elastic strain, and so this part will be on plastic strain. So here the same thing, and this one we use the displacement and we use the load, and so this is called this area. This is so this will be called elastic displacement. So from here to here will be the plastic displacement, and for this area we also use this is elastic area. So this area is called the plastic area, right? So JPL equals eta is a vector multiplied by APL, and if you do the experiments, and you should have this figure, right? You can just easily get this the area of APL. BN is the net thickness for the side root is specimen. And B0 is initial ligament length, ligament. Width is W, crack length is A. W minus A is the ligament length. So we use this equation to get this JPL. And for this eta, and how can we select the eta? And the selection of eta is dependent upon what kind of specimen you are using. For example, for a single edge notched the bending specimen, eta we use 2. However, if we use a compact specimen, as I said, compact specimen is a specimen we use in our the quiz modeling. If we use that specimen and we use this equation to get the corresponding eta, and as I said, B0 is initial ligament length, which equals W is width minus the crack length, and this W itself is the width. So there is an observation. The observation says that equation 710 and equation 11 do not correct the J for crack growth, but are based on the initial crack length. So this is you should know that. Okay, so if there's a need, you should know which equation you can get and how to calculate the J, and from this JEL and also JPL. And JPL you need to do the experiments, and JEL and you can use this equation to get. We will not do experiments, but I still want you guys to know that. And then I'm going to talk about the very, very important procedure to determine the JQ and how to do this is a JQ. I want you guys put a star mark here. I might also test your understanding in our final exam. Well, this is very, very important. As I said, if you get a job in industry or if you go to the graduate school and you are doing some mechanics related research or projects, and you might, if your boss might ask you guys to do something if they have a new material, and to determine, for example, to determine the JC, the critical integral, J integral, and how to do this one experimentally. If you can show your boss that, and you learn this one from Dr. Ma, and the boss will be very, very happy. Okay. So here this figure shows. So this figure shows, you can see this is a crack extension. So here is a J integral, and this is a J integral, and there are several ways. Okay, first way, crack, because we are calculating the crack length, and you can draw 3 lines. Okay, so if you can get this is one, and you draw the 3 lines, and 2 exclusion. This exclusion lines are drawn as a crack extension delta A value of 0.15 millimeter and 1.5 millimeter. So this is 10 times higher. Okay, this one is this one is 10 times higher than this one. And then use the scope. Scope equals M multiplied by sigma y. And sigma y here is called flow stress. And you can see flow stress is the average of yield stress plus the ultimate stress. I want you guys to pay attention to this. Okay? And otherwise, you will be confused. Keep in mind, sigma y in this context, sigma y is different from sigma ys. Sigma ys is yield strength, and sigma y is a flow stress. Even though sometimes we use sigma y to stand for the sigma ys, but in this context, in order to differentiate these two guys, we introduced a flow stress sigma y and these yield strengths and the sigma ys. Right? And you can imagine sigma ys and sigma ultimate strength. So usually for this curve, so this point is sigma ys, the yield strength. Only this is where supposed it goes this way. This is ultimate, and this is sigma UTS, ultimate strength, the highest one. So this is sigma y here, and we just take the in the middle, right? The average. So here we see sigma y, sigma y, and sigma y in this context equals the average of sigma ys plus sigma UTS. And keep in mind, otherwise, and you guys will be totally confused. So after you get these two lines, so this is a 0.15 go here, and 1.5 millimeter go here. After you draw these two lines, okay, and so this is M here. M you can just determine experimentally, or you can just select 2.0. And there is a horizontal exclusion, J max is equals B0, and B0 is initial ligament length. B0 is initial ligament length. It equals W minus A0, initial crack length, and multiply by sigma y and divide by 15. Okay, so use J max and get this, get this line. You have this line, and you have this line, and then you have J max. So we have three lines here. So here is three lines, and all data that fall within these three exclusion limit lines. So that means this line, and this line, and this line. And we fit it, we just fit it, best fit it using the power law expression and using this equation. J equals C1 delta A, and this is a C2. And how to do that, guys? How to do that? And if I trust me, guys, I will not ask you guys to do it, truly. But on how to do that, I'm going to show you. On how to do that, guys, you get all this data and put this data in the Excel sheet, and do this one using Excel. Okay? After you use Excel, Excel can do this one automatically. You have delta A along with the J, and you just tell the Excel the software that you want to and best fit this data using a power law expression, and then they will do this one for you, and then they will tell you these two constants C1 and C2. You have sense, guys? Okay, the third step is GQ. The GQ is defined as the intersection. The GQ is defined as the intersection between this one, you just specify it, and the 0.2 millimeter offset line. The 0.2, we have at the very beginning, we have 0.15 exclusion line, but just a little bit away from this 0.15, and we can have another line, 0.2 millimeter, and we draw a line that is parallel and to this exclusion line, and which also has the same, this is the slope M sigma y, and then this line, and this is the best fit line, and they have intersection. So this one intersection is the GQ. Right? Now this is only the GQ, guys, and then you need to check, and if this GQ equals JC, JIC, or no, and how to do that, guys? And then you need to check if the thickness B and also the initial the ligament length B0, if both of them are less than or equal to 25 JQ divided by sigma y. If this inequality is satisfied, we can see that GQ, we assign GQ to the JIC. And you can just tell your boss that these experiments are very, very successful. I get the JIC for you. That's a GQ. Okay? This experiment is very good. However, if this inequality is not satisfied, this is GQ. GQ is not valid, and then you need to use a bigger size specimen to redo. Okay, so this happens. This happens because if we are given a new material, I do not have idea whether this size of the specimen is good or not, right? This is the try and error, trial and error is a process. Do you guys agree? If we are lucky and for the first shot, I hope okay, the GQ is valid. So that's very lucky. But usually, we are not that lucky. We will do several iterations, increase the specimen a little bit more, until so this inequality is satisfied. Okay, why should we do that, guys? But at the very beginning, if we have a new material, usually the new material because it's new, the price is very high, very, very expensive, right? As a result, we always prefer to use a smaller one, a smaller specimen, and to do the test. However, if sometimes we use a smaller one, but sometimes under these circumstances, the GQ is not valid. What should we do? We should use the smaller one at the very beginning, and if we are very lucky, first shot we succeed. Otherwise, and we just increase the size of the specimen and do the same thing, follow the same procedure, and then double check whether this inequality is satisfied or not. If yes, stop, and we are okay. Otherwise, we need to do the next iteration. You have yes? Okay, so for the exam 7.1 and exam 7.3, and you can exam 7.1 is for the KIC, okay? Exam 7.3 is for the JIC. We know JIC and KIC, and they are different, and so be very careful. And so we have very, very similar this equation, this inequality, but they are different. And there are two different sets of inequality. One is for the KIC, one is for the JIC. You can just, if you are interested, you can just browse the handout I gave you before, okay? Which talks about how to get the JIC. So we can see that B required to get GIC is nearly 2 orders of the magnitude lower than the specimen dimension that ASTM E399 requires for this material. And thus GIC size requirements are much more lenient than the KIC requirements. So ASTM E399 for the KIC, so here 8020. So here is a E8020. So you can see I'm using different protocol, and we might have different requirement for the specimen. That's the reason when you finish your experiments, when you report your findings or in the published paper, when you publish a paper, you must tell people what procedure you use. Okay? Otherwise, some people will question, hey Bobby, what kind of protocol you use? Because I use the E399, but my value is different from yours. And then Bobby should clarify, oh, you use the E399, I'm using E1820. That's the reason. Okay? So, and to be a very, very good researcher, and we need to be very, very responsible when we report something. If there is no need to hold these some secrets, and we are supposed to tell people everything. Okay? However, if there is some business interests, financial interests, you can hide. You can hide. But if there is a need, and you need to provide. Otherwise, you will be in trouble. But you will not necessarily to provide the secret and to the people who ask, but you're the questioner, and they will ask your funding sponsor, and to verify this. Okay, you know what I'm saying? Then the sponsor will ask you. Then you provide all the details to the sponsor. Then your sponsor will tell the questioner that, oh, we have already verified this, but for the financial interest, we cannot tell you. That's okay, totally fine. Okay. To be a good researcher, and we should be ready and to share everything with the questioner. Understand, guys? Now, I will in the final exam. I'm going to ask you guys. Okay, I'm going to give you hypotheses and give you these. Just suppose we are doing some. I'm doing some the GIC experiments. I will ask you guys. What ASTM protocol I should use? And if you select this one, you should tell me why. Okay, and then what is the procedure? And for here, if I ask you guys, suppose I have a new material, so this new material is very new. I just created yesterday. I want you guys to tell me the procedure and to get the GIC. Then you tell me what's the ASTM protocol you are going to use. Why? And then tell me the procedure, the steps. And then tell me how can you tell people that your final results is reliable? This is through these hypothetical experiments, I can test your understanding of this procedure. What? It's very useful. The fractional mechanics is very, very useful both theoretically and also practically. I think you might be asked to do some of these kind of things either in the graduate school or in your industry, in the industry. Any questions so far? We have 4 more slides, and we have 4 more these lectures, and also after we finish the last one, I'm going to give you the example of how to use the Paris law to calculate to solve the fatigue problem, and then we finish everything. Then after I give you the final exam, and I also based on the survey, and some students said I ask you guys, do you think for the final exam and the redo policy is helpful for you? And some students say yeah, and they like the redo policy. Oh, okay. So then we will follow this redo policy again for the final exam. Okay. That means I will give you some hours, and you finish the final exam first. And then I will grade, right? Then I will send them back, and I'll give you option. You can just redo, work on this is the problems that you have lost the points on, and then submit yours, your new one. Then I can give you 50% back. This is optional, and you can just select no. Okay, it's optional. And then I just grade everything, finish everything, and post and final grade on the Canvas. Okay, so this is pretty much what I have today. You need to be serious, okay, about this one, because the GIC, KIC are very, very important. The concepts for the fractional mechanics also, and they are very, very important parameters for any materials. And whenever you buy some materials, materials. And you will always check these 2 guys to know what is the toughness it is, and how much energy this guy can absorb before it fractures. Okay? GIC, KIC are most important concepts in the fractional mechanics. So I will test your understanding of this. As I said, I will give you hypothetical material and ask you guys which protocol we should use, why, then how, and then finally tell me how you can convince people that the JIC is reliable. This is what I want to know. I will give a hypothetical material and to test your understanding of this. Then you should, whenever you see this problem statement, and you know, so this is the lecture 26 for the handout. You can get the results. But I say that because this is lecture 26 for the handout, but for the lecture room, and so this already, I think already 30, 34, 35 or something, right? Be very careful. Any questions? Without any question, and I'm going to end today's session. So I can give you 9 minutes. If you have, you can just work on the homework board. You can do something else. And anyway, by this Friday evening, let's be 9:00 p.m. Give me the homework board. So Friday evening or the early Saturday morning, I can grade.